example number 4, we're going to solve these problems the reverse, So rather than solving a differential equation, we're given the solution to the differential equation. They're asking us, what equation does that solution correspond to? Okay, so one thing you might want to observe about these two, number 1, letter A. We have a linear combination of exponentials. And actually you can see the coefficients of x in the exponents are real and distinct values. So that's actually a case for the linear, for the non-repeated and real. Okay, so that means, what is that, like m equals to -3 and m equals to 4. So what does that mean? This means m plus 3 equals to 0 and m minus 4 equals to 0. So from here I'm going to go backwards, zero product property. All right, so that means m plus 3 times m minus 4 equal to 0. And, well, just multiply FOIL m squared minus 4m plus 3m minus 12. And this is equal to 0, and simply combine like terms. So this would be back to the characteristic equation, or the auxiliary equation, however you want to call it. All right? But we want to look for the differential equation that does this. Well, how do we go about this one? We turn a differential equation into an algebraic equation, right? So now we're going to do the reverse. An algebraic equation turning into a differential equation, and that'll be our final answer. All right? So when it comes to something like this, like, what is that? Like linear repeated, or even the linear distinct, or even linear repeated, this is relatively easy to compute. What about when it comes to a case where we have linear combinations of exponentials with trigonometric? Well, so number 1, by looking at this solution, look at the coefficient of the exponential and look at the coefficient of, the coefficient of the trigonometric, the angle in the trigonometric rather. Well, so this tells us alpha equals to -1, and this also tells us beta equals to 9. All right, so this means m, the solution to the equation, is equal to -1 plus 9i, or rather plus or minus 9i. And well, it doesn't matter where did this come from, by maybe an interesting factorization, completing the square, or using the quadratic formula. Who knows? All right, who knows? Well, how do we go backwards about this one? Well, this one is going to be a little trickier. Okay, so check this out. All right, so this is the same as saying m, what is that going to be? So m minus -1 minus 9i on the one hand, times m minus -1 plus 9i, and let that be equal to 0. All right? Let me clear the parentheses inside of each group of brackets. That'll be m plus 1, plus 1 plus 9i, and m also plus 1 minus 9i. All right? So from here, from this multiplication of parentheses, we're going to go back to the polynomial equation, giving us the solution. However, think about this one, guys. Okay, check this out. So what would you do about this one? Would you do all this and then all this multiple times? Would you do that? Is that what you... Okay, no. That's not how we're going to do this. Check the trick. All right? So do you guys agree That's the factor form of a difference of squares somehow. This is, you have n plus 1 and n plus 1, and you have plus or minus 9i. All right? So this is the same as saying, using a difference of squares, n plus 1 quantity squared minus 9i quantity squared equals to 0. Okay? Let me use a different color to represent the b part. Okay? All right, well, I mean, how about we expand the binomial? That's m squared plus 2m plus 1, and 9 squared, which is minus 81, times, what's negative 1, what's I squared? Isn't that negative 1? Negative 1, so let that be equal to 0. Okay, and well, negative times a negative, isn't that positive? 81 plus 1, that's m squared plus 2m plus 82 equals to 0. So that's the polynomial equation that would give us those complex solutions. Of course, we would use, maybe the quadratic formula, right? To get back to this. Now we need to get the differential equation. Y double prime plus 2y prime plus 82y equals to 0. So that's the equation whose solution is given. All right? Okay. So, example number 5. There's a couple more exercise, a theorem here and there. Okay, so, suppose the solution to a differential equation is given by y equals to 2e to the negative 3x plus 3e to the 4x. Similar to what we have over here, but with some C1 and C2 out there. All right? Okay, so let's see. With initial conditions, y of 0 equals to a and y of 0 equals to b. Okay, so we don't know what a and b. So they're asking us for the values of a and b, that evaluating the conditions would give us the coefficients 2 and 3. All right? So, how do we go about this one? Okay, so number 1, let me actually take the derivative. Y equals to negative 6 e to the negative 3x plus 12 e to the 4x. Okay, that's y prime. All right. So let's evaluate y of 0. So y of 0 equals to 2 e to the negative 3 times 0 plus 3 e to the 4 times 0. What's y of 0? Y of 0 in this case equals to a. A equals to 2 e to the 0 is that one, plus 3 e to the 0, which is another one. So a equals to 5. All right. A equals to 5. All right, we're going to do the same for the derivatives. Y prime of 0 equals to negative 6 e to the negative 3 times 0 plus 12 e to the 4 times 0. And y prime of 0, well, actually that's b. Okay, that's b equal to negative 6 times 1 plus 12 times 1. And b equals to 6. So that means y of 0 equals to 5 and y prime of 0 equals to 6 will give us that particular solution. All right? Okay, guys, there's one more piece of information. Okay, the next piece of information is the notation, the big D notation, which is a differential operator. That's something we're going to get more in depth at the end, almost at the end of the chapter, or maybe at the very end of the chapter when we look at the operator method to solve differential equations. Okay, so there are many ways to denote a derivative, like y prime, f prime, dy dx. Another operator is an uppercase D, kind of like multiplying with the dependent variable. It's really not a multiplication. This is really like an operator acting on a function. And well, the operation actually performs an instruction. What is that instruction? Finding the derivative of y with respect the independent variable. The disadvantage of this notation, however, is that it's not clear usually what's the independent variable, but at least we know what the instruction is. Well, so the second derivative, it's the same d raised to the second power, kind of acting on the dependent variable, and of course d cubed y, d to the fourth y, that's the third derivative, the fourth derivative, etc., etc., etc. All right? Okay, so example number 6. So express the differential equation y triple prime minus 2y double prime plus 9y prime minus 18y. Okay, so all we need to do is say simply d to the third power minus 2 times d squared plus 9 times d minus 18. All of this simply acting on the function y. So that's all we need to do. All right? Just represent. And the reason why I'm going over this is because some of the homework questions have this notation, just so you know what to do in a situation like that. All right? So, I mean, this actually gives us a better visual of what the characteristic or auxiliary equation is, because what do we do next to solve this equation? Write the equation in terms of n and solve it by either factoring, the rational root theorem, or whatever requires. All right? So, yes, looks like this is the end of the section, all right?